જેની વાતે તેના અવિત્રવતો.
Good morning. Analytical chemistry is a branch of chemistry which deals with analysis. So when we speak of analysis, we think of the various analytical methods that are available. Now, whenever we want to analyze a sample, the first step that comes is sampling. After procuring a sample, the next step is processing of the sample, that is converting it to a solution form or whichever form it is required for the particular analytical method that will be decided later. Now, whenever we deal with real samples, it is not the element of interest that you are looking for. For example, if it is a silver ore, it will not be silver alone which is present there, but along with silver there will be other elements also associated. Now, since we are interested only in the silver part, we have to resort to a method by which you will be able to isolate silver from the rest of the elements with which it is present. So, therefore, in analytical chemistry, selection of method is very, very important. But before that, separation, isolation of the element of interest from the rest of the interfering elements is equally important. Now, there are various separation techniques which are available. So, basically, our topic of discussion is separation methods. Out of the separation methods that I will be enlisting to you, we will be concentrating only on the solvent extraction. Now, the very, very crude, supposing you have a solution where there is sand and water. Yeah, you want to separate out the sand from water. What will be the method that you will resort to? Filtration or even decantation, because sand is very heavy. So, decantation will help out. You have got a precipitate in the solution and you want to isolate that precipitate from the rest of the solution. The method that you will resort to will be a simple filtration using a filter paper. Yeah. Now, supposing you have mixture of liquids varying in boiling points, the method that you will adopt to separate them will be distillation. Yeah, because difference in the boiling point of the different components that are present. Solvent extraction is one of the method where the basis of separation is difference in the solubility of the solute in the two indivisible solvent. One of the major methods in analytical chemistry is chromatography. In chromatography, the separation is due to the differential migration of the solute across the stationary phase. So, there is a competition between the mobile phase and the stationary phase. The one component which has got more affinity for the mobile phase will move forward, the other one will be retained with the stationary phase. So, chromatography, there are various types of chromatography. Then we have electrophoresis, where the electrical property, the species should be electrically charged and the migration of the electrically active species towards the in the electrical field is exploited. There has to be a difference in their migration rates. Yeah. Then in ion exchange chromatography, it's a special type of chromatography where ion exchange resins are used. So, the different affinity for the solute towards the ion exchanger is the basis of separation in ion exchange chromatography. Now, since we are going to be only looking into solvent extraction today, we will try to understand what is solvent extraction in detail. Now, solvent extraction. also known as liquid extraction. As the name itself suggests, extraction of the solute into the solvent. Extraction of the solute present in the liquid, because it is liquid extraction. So the solute is present in the liquid state or in the solution state, and it is going to be extracted into another solvent. The definition of solvent extraction goes like this. When a solution, usually aqueous, is brought into contact with another solvent, essentially immiscible with the first, in order to bring about the transfer of one or more solute from the aqueous phase into the organic phase. Okay? Now, the reverse also can happen. Suppose you have prepared an organic compound, then if you want to isolate that, you will be treating it with a solvent in which it will become soluble. So, organic compound, it will go into the organic phase. Reverse also can happen is, if you want to bring from organic phase the solution to the aqueous phase, that is also possible. The other way around also it is possible. Now, having understood this, liquid extraction, that is extraction of the solute from the aqueous phase into the organic phase. What are the advantages of this particular technique? The separations are very simple, rapid, convenient. It can be done in a very simple type of an apparatus, the separating funnel. It's applicable to samples in the trace level of concentration as well as in the macro level of concentration, and it finds wide applications in the nuclear processing, ore processing, refineries, and you name it, and solvent extraction is widely employed. Now, before we go further to understand the principle behind the solvent extraction process, I will demonstrate to you one classic separation of ferric and magnesium mixture. What we are going to do here is a mixture containing ferric and magnesium. Using the solvent extraction technique, we will be separating the two elements from each other. Alright? I will call Yash to assist me in this. This is the mixture which is ferric and magnesium. Now this is taken in 6 molar HCl. 6 molar HCl, why 6 molar HCl? Why not 4 molar? Why not 7 molar? Because in 6 molar HCl, quantitatively the entire ferric is present in the form of a complex, that is H plus FeCl4 minus. And what is the peculiarity of this complex? This complex can undergo extraction, or it can solubilize in oxygen containing solvents. Oxygen containing solvents, meaning thereby ether, then esters, ketones, high molecular weight ketones, all those oxygen containing solvents, this can be extracted. Now what we are going to do, we will transfer this solution containing ferric and Mg. Now ferric is not in ferric form, it is present in the form of that particular complex. Okay. Now we will add into this 10 ml of ethyl acetate. just we will swirl it, not shake it vigorously because ethyl acetate has got some solubility in water. Generally, we can use ether also for this purpose, and ether does not have lot of solubility in water. But ether has got advantages. Clear its separation, its boiling point is 37 degrees centigrade. But one major disadvantage with ether is the naked flame should not be there anywhere around, and it produces the anesthetic effect, anesthetic as well as toxic effect on the person who is working with it. Yeah, you can clearly see that the iron, major part of iron has gone into the organic phase and quite a lot has remained here. Yeah, so what we have to actually do, separate the phases. The lower aqueous will go into the second separating funnel. The upper organic will remain in the first separating funnel. Then subsequently, the second this aliport, that is the aqueous phase, will be treated with one more aliport of ethyl acetate, the solvent, and then once again the equilibration will be done. Equilibrium has to reach between the organic phase and the aqueous phase, and subsequently in the third separating funnel. By the end of the third extraction, we will find that the upper organic phase will be practically colorless, indicating that the entire iron from the aqueous phase has been now transferred. Is it clear? So you can just show this phase separation, and we need not perform the next two extractions. Fine. Thank you, Yash. Is it clear? So, solvents play a very important role in the transfer of the solute. Which solvent we choose also is very, very important. We shall see it at a later stage. Now we will concentrate on the principle by which this particular process is happening. The principle is Nernst distribution law. Nernst distribution law. Whenever a solute is equilibrated between two immiscible phases, provided the temperature is constant and the molecular state is same in both the phases, the ratio of concentration of the solute in the organic phase to the ratio of the concentration of the solute in the aqueous phase is a constant called as the distribution coefficient or partition coefficient. We can show it K, we can write it as KD, or we can also write it as KPC. PC means partition coefficient, D means distribution coefficient. So KD is equal to concentration of, let us say we are dealing with species A, so concentration of A in the organic phase to concentration of A in the aqueous phase. It's very important. See, look here, this is a separation technique. So we will not have a single component, and we are always going to have minimum two or maybe even more. So in the example that we saw, the demonstration experiment, we had two components. We had ferric and magnesium, which were required to be separated from each other. So which one underwent the extraction? Fe went the extraction. Fe underwent the extraction. Mg, since it didn't form any complex, it remained in the aqueous phase. So if you consider Fe as that particular A component, so concentration of A in the organic phase to concentration of A in the aqueous phase. Practically in the aqueous phase there is no iron, but it cannot be zero. It can never be zero. There may be 0.0001 gram of the iron present, which we are not capable of detecting with our usual analytical tools, the regular analytical tools. So, this is the Nernst distribution law, is it understood? Now, this particular law is not thermodynamically rigorous because it is speaking about the concentration but not taking into account the activity of the species. Activity of the species is concentration multiplied by the activity coefficient. Yeah, it is not thermodynamically rigorous. So, secondly, whenever the molecule under consideration undergoes any kind of association or dissociation, this law cannot be applied because for applying this, the molecule has to be there in the same molecular state. Yeah. So, what's to be done now? Now, analytical chemists are very smart. For everything, there is a solution. So, since we are dealing with very dilute solution, activity coefficient, the ratio of activity coefficient is unity 1. Yeah, and we will not worry about, we are not worried whether the molecule is undergoing association, dissociation, complex formation, any kind of transformation. We are only interested that particular A under consideration should get transferred to the organic phase in whatever form. Yeah. So, therefore, we modify this Nernst distribution ratio, Nernst distribution law in a sense, we make it distribution ratio. Distribution, instead of calling it partition coefficient or distribution coefficient, we will now call it as distribution ratio, which is written as D is equal to concentration of solute, very important, in all its forms, irrespective of any form in which it is present, in all its forms in the organic phase divided by concentration of solute. I will put it concentration of solute A, specifically we are talking of A in all its forms in the aqueous phase. So, once again, D is equal to A, concentration of A is the organic phase upon concentration of A in the aqueous phase. Alright? So, for all practical purposes, we always talk about distribution ratio only, not distribution coefficient. We are not very worried about its thermodynamics. We are not very whether it is undergoing any kind of change in its molecular state. Alright? Now, here we have chosen ethyl acetate as our solvent. Now, how to make the choice of the solvent? Very important. Now, the solvents are of two types: polar solvents and non-polar solvents. Now, polar solvent, water is our classic example. Yeah, how the water molecules are bound to each other because of the hydrogen bond. Similarly, you have ethanol, you have methanol, acetone. All these come under the category of polar solvents. Non-polar solvents, you have host of hydrocarbons, then you have esters, ethers, yeah, chloroform, carbon tetrachloride, all these are non-polar solvents. Now, the thumb rule is like dissolves like. So, whenever you have a non-polar solute present, it is going to be dissolving in the non-polar solvent. Correct? Now, can we use a polar solvent to separate out a solute which is non-polar? We cannot use. As it is, most of the polar solvents we will find, they are miscible with water. So, they cannot be used in solvent extraction. All the solvents which we have listed like ethanol, methanol or acetone, all of them are miscible. We cannot use them. So, the non-polar solvents are majorly used in the solvent extraction methods. Now, again, depending upon the solubility, there has to be a differential solubility. Suppose there are two components, one of them should be much more soluble than the second component. Only then separation can happen. So what is important when making the choice of the solvent? The D value of the solute should be very high towards the solvent which is chosen. D value should be very high. Secondly, when we defined the solvent extraction, we said it should be immiscible. So there has to be a large density difference between the aqueous phase and the chosen solvent. Like chloroform or carbon tetrachloride, they are having more density, so they will be forming the lower layer. Now the example that we demonstrated here of iron and magnesium separation, in that we use ethyl acetate. Ethyl acetate is like forms the upper layer. If you use toluene, it will form the upper layer. Yeah. So very important is what? It should be having there should be a great density difference between the aqueous phase and the organic phase. Yeah. Then it should not be very toxic. It should not be flammable. Therefore, generally, though ether is a very good solvent, we try to avoid the usage. Here we compromise. Ethyl acetate has got some solubility, but fine. Still, ethyl acetate is preferred over ether for all practical purposes. Then, it should have low viscosity. The solvent chosen should have low viscosity, because otherwise, at the interface, emulsion will be formed. You will not get clear-cut two layers separated. And finally, very importantly, we should be able to recover the solute from that organic solvent. Yeah. Now, recovery of the solute. For recovery, we use backstripping method. Backstripping is reverse of solvent extraction. In solvent extraction, what we have done? We have transferred the solute from the aqueous phase into the organic phase. In backstripping, what we do? We bring back the extracted solute from the organic phase into the aqueous phase. Now, in this particular case, once again, I call upon Yash. This is the extracted iron. Yeah. This iron now we want to estimate. We want to estimate this iron present in the organic phase. So we will use a backstripping agent. Now, how to make the choice of the backstripping agent? We start with water, universal solvent, water. Then we can try dilute HCl, we can try dilute NaOH, dilute ammonia, various different types of buffers. They are all tried. It's basically a trial and error method. Yeah, in this it's already tried and tested. Water is the best backstripping agent. We have to add water. I brought distilled water in this. He added 6 molar HCl. You found that there was no backstripping which happened. In 6 molar HCl, the backstripping cannot happen. Slowly. Slowly. So 2 or 3 times we will do it. So from the organic phase, because he has added 6 molar HCl, there is some little problem here. But never mind. You can see the color has diminished in the upper layer and the entire color has come in the lower layer, which is distilled water. Fine. So again, after removing this out from the separating funnel to the upper organic phase, we will add 1 more aliquot of distilled water and backstrip the entire iron which has undergone the extraction. Okay, fine. So recovery of the solute then by backstripping method. Now supposing there is a complex like nickel DMG which itself has got a color, yeah, we can adopt direct spectrophotometric method. Whenever there is a metal complex which is being extracted having a chromophoric group, so either it will be UV absorbing or absorbing the visible region, we can do direct photometric method. That is got an added advantage, because during the backstripping process, some loss can happen. But here what is happening? You perform the extraction, draw the organic phase out, directly subject it to the spectrophotometric method. So that is about the principle of the method. Now next we will see efficiency of extraction. I hope everything is clear. Now efficiency of extraction. Can be determined, or we can talk about the efficiency of extraction in terms of the weight of the solute that has undergone the extraction. Weight of the solute. Now once again, when we do the research work in solvent extraction chemistry, we know that the metal is undergoing the extraction, but whether it has gone 100% or not, no doubt we do the estimation in the organic phase, and the remaining aqueous phase is also tested for the presence of the metal. If it is present, that means quantitative extraction has not happened. If it is present, to what extent it is present, that is also determined. So efficiency of extraction we can talk about in terms of the amount extracted or amount remaining unextracted. Another thing is efficiency of extraction increases with the number of extractions. Multiple extraction with smaller volume of organic solvent is more efficient as compared to single extraction with a large volume of the solvent. In this specific case also I told you, we are removing the lower aqueous phase, taking it to next separating funnel, treating with fresh portion of the organic solvent. Once again equilibrating the two, it will go to the third one, and finally we achieve the quantitative separation. 99.99% of the iron would have undergone extraction into the organic phase. But if we had done it only once, then it would not happen. And the extent of how much it has happened will be totally depending upon the distribution ratio of that particular species towards that particular solvent. Now, efficiency of extraction, now for proving this point that multiple extraction is more efficient as compared to the single extraction, we will consider the solute A, whose weight is W gram initially. W gram of species A is present in, say, VDM cube of the solution. Volume of the solution in which it is present is VDM cube. After equilibrating it with VODM cube of organic solvent, the amount of A which is left behind is W1 gram. Okay, so W gram of the solute is initially taken, present in VDM cube of the solution. It is shaken with VODM cube of the organic phase, and the amount left behind at the end of first extraction is W1 gram. Alright, putting it in the expression for distribution ratio, D is equal to concentration of the solute in organic phase in all its forms, that is understood. So D is equal to concentration of the solute in the organic phase divided by concentration of the solute in the aqueous phase. So what is the concentration of the solute in the organic phase? W1 has remained unextracted, mind you. So out of the W which is taken initially, you see, W1 is remaining weight. That means how much has gone into the organic phase? W minus W1. So W minus W1, and it is present in what volume of the organic phase? VO, DM cube. Okay. Now divided by total concentration of solute in the aqueous phase. Aqueous phase, how much is remaining? W1 gram is remaining. So W1 gram in what volume? V. Okay. Now further, W minus W1 multiplied by V and W1 multiplied by VO. After cross multiplying, we get D W1 VO is equal to W minus W1 into V, and after solving it for W1, we get it W1 is equal to W V upon dVO plus V. This is one of the very important formula for finding out how much weight of the solute has remained unextracted, or provided you have a lot of numericals to solve in this using this particular formula. So you may be given, sometimes you may be asked to find out the W1, you may be sometimes asked to find out D value. All of this known, then will be unknown. Right? Now this is single extraction which has happened. Now the same solution containing now W1 gram of the solute. Are you understanding? Initially we started with W gram. After doing equilibration with VOD into, how much went into the organic phase? W minus W1, leaving behind W1 in the aqueous phase. Now this W1 is going to be treated with the second alcohol of organic solvent, once again VOD into. Right? So what will happen, since it is a second extraction, it is W2 is equal to W1 V upon dVO plus V. Right? Now substituting for W1 from this expression, what you will get? Substituting for W1, you will get W2 is equal to W V upon dVO plus V raised to 2. You do it for the third time, you get W3 is equal to W V upon dVO plus V raised to 3. You do it n number of times. What do you arrive at? Wn is equal to W V upon dVO plus V raised to n. This is the formula to be employed whenever it's a multiple extraction system. Alright? So, multiple extraction is more efficient. Multiple extraction using smaller volume of organic solvent is more effective as compared to a single extraction using larger volume. The same point we can prove it in one more different way. I'll show you that. W1 is equal to W V upon dVO plus V. Now, instead of writing VO, we will write NVO. I'll tell you why. D NVO, and instead of writing W1, we will write it as W dash N. Actually, it is W1 only. But why we are doing this kind of thing, I'll tell you. Suppose we have 50 ml of this solvent at our disposal. Okay, we have two options. One is to use all the 50 ml in one single extraction, or to use this 50 ml in 5 extractions, 10 ml each. Okay, so when I talk about NVO, what I mean is, here it is NVO, means all the 50 ml in one go. So it is N into 10. In this case, N is 5. So 5 into 10 means 50. I am going to use 10 ml in each extraction. So how many times I am going to perform the extraction? 5 times. Here only 1 time. So this is N and this is VO. Since this is the VO, therefore we have written the formula N. Alright. So W. Now what we do? We divide the numerator and denominator by V. So when you do it, 1 upon dn VO by V plus 1. Alright? Further, W. Now we put dVO by V equal to X. dVO by, since dVO by V is equal to X, W 1 upon Nx plus 1. This is the scenario where entire volume is used in 1. Now, suppose it is used in n times it is used, then the formula that we use is Wn is equal to W V upon dVO plus V raised to n. Now, Wn is equal to W, once again dividing the numerator and denominator by V, we get 1 upon dVO by V plus 1 raised to n. Now dVO by V, we have taken it equal to X. So Wn is equal to W 1 upon X plus 1 raised to n. Right? Now looking at these two equations, which is greater? X plus 1 raised to n is greater or nx plus 1 is greater? Which is greater? X plus 1 raised to n is greater. Since this is greater, this is going to be lesser. So, since x plus 1 raised to n is greater than nx plus 1, it follows. What follows? It follows that w dash n is greater than w. Means, once again, what point we are trying to prove? That using smaller volume of the organic solvent more number of times is more efficient as compared to single extraction. Is it clear? Now, extraction efficiency we also talk about in terms of percentage extraction. Percentage extraction. How is the percentage extraction defined? It is defined as percentage extraction, or simply it is written as P is equal to fraction of the solute extracted multiplied by 100. Fraction of the solute that has undergone extraction multiplied by 100. Now consider single extraction system. Single extraction. What is the formula? We know W1 is equal to W V upon dVO plus V. This is for the single extraction. Now fraction of the solute extracted. When we derived the formula earlier, this particular formula, yeah, we have taken the initial quantity of the substance as W. Out of that, W1 is unextracted. So W minus W1 is extracted out of total W. Out of total W, only W minus W1 has undergone the extraction. Multiplied by 100 is your percentage extraction. Now substituting for W1 from this expression, what we write? We write W minus W V upon dVO plus V whole thing divided by W into 100. W get cancelled and you arrive at 1 minus V upon dVO plus V. On solving this, what do you get? You get multiplied by 100, of course. On solving this, you get percentage extraction is equal to dVO upon dVO plus V. P plus V upon VO multiplied by 100. This is another important formula to calculate percentage extraction, provided you know the distribution ratio value and you know the volume ratio V upon VO. So, percentage extraction is directly proportional to the distribution ratio. It is inversely proportional to the volume of the organic solvent and directly proportional to the volume of the aqueous phase. Okay. Now this is for a single extraction. Percentage extraction formula for a single extraction. Consider for a multiple extraction, same formula, fraction of the solute extracted multiplied by 100. Here what we are going to use? Wn is equal to W V upon dVO plus V raised to N. Alright. Percentage extraction is W minus, it will not be W1, it will be Wn upon W. W minus W V upon dVO plus V raised to N upon W, and you get it as 1 minus V upon dVO plus V raised to N into 100. This way in which we solve for single extraction, we cannot do that because there is exponential factor. Therefore, this is percentage extraction. So finally, what is the formula for percentage extraction? This is the formula. 1 minus V upon dVO plus V raised to N multiplied by 100. We can put it in a square bracket. So this is the formula to be used for the multiple extraction system when we want to find out the percentage extraction. Okay, thank you very much. So what we have learned today, that solvent extraction is one of the very important tools in analytical chemistry for separating the solute from the solution when it is present along with some other elements. We also learned that distribution ratio of the solute towards the chosen solvent and the temperature is very, very important. D will be constant only if the temperature is constant and the solvent is the same. If you change the solvent, like for example here we use ethyl acetate, suppose we use some other ketone, maybe the D value will not be the same. D value will change as per the solvent which is chosen. We also learned that whenever we do the extraction, multiple extraction using smaller volumes are more efficient as compared to single extraction using the entire volume in one go. And finally, we learned that percentage extraction is very important. Percentage extraction can never be 100%. It can be 99.999, but it cannot be 100%. It is just that we feel it is 100% because we are incapable of detecting that very small amount of solute which is remaining behind. So, when writing the thesis in the solvent extraction, if somebody writes 100% extraction, a serious objection should be raised because it cannot be 100%. It can never be 100%. That's all. Thank you very much.